Okay, this next video is going to move from where we left off in the GCSE video about circuits, and I think we covered the introduction to electricity for GCSE. And in this video, I'm going to start off with the GCSE summary for circuit rules, and I'm going to go right up to A-level standard for students who either want to be stretched in GCSE, but mainly also for students studying A-level, and those doing international A-level. This will be from Unit 2, and it will go right up to potential divisors, resistivity, drift velocity of electrons. Okay, so the beginning is good for GCSE, and GCSE students who are doing higher level may find this a very interesting video to stay in until the end. Okay, so I hope you like the extra videos I'm putting up, as I have a bit of spare time this weekend due to half term. I'm putting a lot of my videos, one of my PowerPoints up on YouTube, so people can look at them from not just our school but all schools. So if you find it useful, please do show your support. Like each video you watch if you found it useful. Even if you learned one thing from it, give that a positive like, because that means the channel becomes more popular and it helps with the algorithms for YouTube. Okay, so the GCSE rules for the summary were as follows. For series circuits, the current is the same at any point, but the voltage splits up over each component. And then in parallel circuit, the current splits in each strand and then joins up again when it comes back to go back to the battery or the power supply. And the voltage is the same across each parallel strand. So these are where we left off the last video. I also gave these problems for GCSE students to try and solve. And if you want to try and write your answers out in the comments below in the YouTube video, see if other people agree with you, from A1, A2, A3, V1, V2, V3 for example 1, and then the second one, which is with 5 bulbs in it, 3 in the first strand and 2 in the second strand. So if you can work these out and see if you can assess each other getting the same answer. So these circuit rules are actually called Kirchhoff's first law for current and Kirchhoff's second law for voltage. And this is what we call it when we go into A-level standard, but it's exactly the same as GCSE. So this was Gustav Kirchhoff. So this is from the 19th century, where they worked out the sum of the currents leaving a point is the same as the sum of the currents entering that point. Basically means what I told you before, that in a parallel circuit, the currents will split up and then rejoin. So you've got to just add up the currents in all the strands, and they will add up to the total current that you started with. Okay, so for example, the GCSE standard would be if you got 6 amps going back into the battery and 4 amps went into the single bulb route, and there would be 2 amps left for the double bulb route. And the reason for that is the double bulb route is double the resistance. So if you multiply the resistance by the current, you will get the same voltage as the voltage of the power supply for each path. Yeah? So think about it, because this will help you solve the problems on the previous slides which I showed you. Yeah? So it's basically an application of Kirchhoff's rules, yeah, which is the circuit rules I went through for the GCSE students. Okay? And it'll then add up to 6 amps. So that's the current in parallel is Kirchhoff's first law. And then when you're looking at electromotive force, when a battery or a power supply provides the energy for a circuit or provides the voltage for the circuit, the potential difference is how you measure it with a voltmeter, and it could be across any components. So it says components like batteries and power supplies provides the force that pushes the current around the circuit. We call this the electromotive force. So they're actually calling it a force. It's not measured in newtons, it's measured in volts. Okay, so it's technically not a force as such. Other components like bulbs, motors, resistors, etc. have work done to them, electrically speaking, by the current, and the voltage across them is called the potential difference. So whenever you're measuring a potential difference, it's just a voltage, and you need a voltmeter to be able to do so. So you could put a voltmeter, for example, across the battery, and that will measure the sum of the EMFs. That's only actually true if you do A-level to the end of the Unit 2 course. You realize that there may be some internal resistance, and you lose some of your EMF as lost volts within the internal resistance of the battery or the cell themselves. Hope that makes sense. So what will happen if you then measure the voltage across the components outside the power supply? Well, the answer is written for you there. So the sum of the voltages providing the EMF will be equal to the sum of the PDs lost across resistances or consumed by resistances. And that would include any internal resistances, for example, inside the battery or the cell. Okay, and this is called Kirchhoff's Second Law. So the definition of EMF is the total work done by a cell is per unit coulomb per coulomb of charge, okay, per unit of charge, okay, which is a coulomb. So this really goes on to Kirchhoff's second law, which he describes as around any loop, that means one part of a circuit which is a complete path, the sum of the EMFs is always equal to the sum of the PDs, okay? That's just the case. You just make sure you haven't missed out any of the PDs, including any resistances which are difficult to define or may not be a component in themselves, but may be an internal resistance of a cell or a battery. Okay, so for example, if you've got these here and the EMF provided is 3 volts for the battery, then the total PDs must be across the 3 bulbs, must also add up to 3 volts. Okay, so if the 3 bulbs or the 3 filament lamps or whatever kind of components they are, if they are identical, they'll get exactly the same share of the EMF, 1 volt each. Okay, so that's a very simple example of Kirchhoff's second law, which was one of the circuit rules we learned for GCSE as well. So up to here, I think any GCSE student would have no problem in understanding the concepts. Resistance also is the same in GCSE as in A-level. Resistance is the ratio between voltage and current. It's the resistance in the circuit, and it reduces the current flow. So if you've got the voltage in volts divided by the current in amps, you will get the resistance in the unit called ohms, named after George Simon Ohm. I believe he was German, and he also lived in the 19th century. So a lot of work on electricity was done in the 19th century, and that's before they had discovered the electron. So that's why we have a conventional current which goes from positive to negative. So they knew that electricity existed, they just didn't have the ability to know what was actually the cause of the charge flow within the circuit. So current was actually defined before charge was defined, if you like. And for GCSE students, if you use the triangle, they'll make it easier for you. You have to remember that I stands for current, not C, okay? I always say it's indicated current because we use C for coulombs, which is a unit of charge, okay? The rest of it is self-explanatory. So up to here, GCSE students will have no problem at all, and you need to know this knowledge. And adding Kirchhoff's law to your understanding just makes sure that you are a step ahead of other high-level students. Okay, so over here, this is just a simple question. So if we've got 2 amps in this circuit, it's a series circuit, so the current everywhere, according to the GCSE circuit rules, is the same everywhere in a series circuit. And if you've got 10 volts across the first bulb, they want you to know what is the resistance across this bulb. So what is the resistance of this bulb, they should say. So it's 2 amps is going through it, 10 volts, so you divide the voltage by the current, yeah, and you will get, because the equation was resistance is voltage in volts divided by current in amps. So the voltage was 10, the current was 2, so the resistance over here will be 5 ohms, okay? All right, and assuming all the bulbs are the same, what is the total resistance in this circuit? Well, if this is 5 ohms, and this is 5 ohms, and this is 5 ohms, the resistance in series, just you simply add them up. So it'd be 5, 10, 15 ohms in total. Yeah? So that means also that this EMF must be enough to give 10 volts to each of these bulbs. So it must be 30 volts, ignoring any internal resistance. Okay? So then they give you problems like this to solve. So they give you the voltage, they give you the current, and you've got to be able to work them out. So again, if you want to try to do these, I'm not going to do them with you. So this is just the kind of problem that GCSE students should be able to work out, because you know the voltage, you know the current in the circuit down here and the one on the right. You've got parallel circuits, so you've also got to work out how you can solve the problem. Okay, so for example, this bulb and this bulb will have the same voltage, so you should be able to work it out. And if the bulbs are identical, then you can assume that they will be treated the same. So I'll leave that for you to struggle with and see if you can work them out. And if there are 2 or 3 of you working together, you can just peer assess each other. Okay? So these are additional questions on resistance. Again, you can stop the video and see if you can use Ohm's law to come up with the answers. Unfortunately, in this slide, I don't think I've got the answers included. Okay? So resistors in series now, as I said, if you've got 2 resistors in series, you just add them up. And the reason is the current is the same through both of them, but the voltage across them could be different because each one will get a different voltage if the resistances are different. Okay? So this is just a part of a circuit. For A-level, you need to be able to show this proof, which I'm going to do now. So total voltage across 2 of them will be V1 plus V2. That's Kirchhoff's second law, yeah? Because it's just divided between the 2 resistances. So the current going through them is the same in both. So in a series circuit, we know that the current stays the same, but the voltage splits up or is shared. So we know the total voltage is V1 plus V2. So now we're going to do some algebra and see if you can follow it. So GCSE students, stay with us because I think you'll be able to cope. If you're going for the higher level grades, this is good training for you. So the total voltage must be the current through all of them and the total resistance of the circuit. Okay? Now we want to prove that total resistance is equal to R1 plus R2 in effect. But since we know that voltage 1 is I times R1 and voltage 2 is I times R2, then we can replace V1 here with IR1, V2 here with IR2, and then we got 2 equations which can then be equated to each other. Okay, so this one, you put these in there. Yeah, so insert for V, substitute for V1 and V2 using I and R, and you'll come up with this equation where I, the total voltage, this substitute on the left hand side, and this substitute on the right hand side of this equation, and this one, and you get I times RT equals I times R1 plus I times R2. The I's cancel because it's the same current throughout. Therefore, you have proven that 2 resistors in parallel are simply the addition of the 2 resistances in ohms. And this applies for any number of resistors in series. Okay? For A-level students, this is a common A-level question. For GCSE students, you just need to know this equation is true. Resistance in parallel, a similar proof is required for A-level students. For GCSE students, they might give you some questions about resistors in parallel. Now, you've got to remember that resistors in parallel, by adding an extra path, you actually increase the total current, yeah? Because there's a current that goes through each path, so you can actually get I1 plus I2, and if you have another path, you can get I3, so the total current being drawn from the power supply will increase the more paths you have. So the total resistance, if you got more current from the same battery, that means you got less total, you got a lower total resistance. So any resistors in parallel actually decreases the total resistance, unlike resistors in series, yeah, to the last slide, where you add resistors in series, you increase the total resistance. In parallel, the more paths you have, the more you decrease the resistance. Okay? All right, so the voltage across the two resistors, because they're in parallel, must be the same. Yeah? So I'll let you read that. I'm just having a sip of tea. So in a parallel circuit, this time the voltage stays the same. This is the GCSE rules that we started the slide with. But the current splits up, okay? So we can do the algebra where the total current must be I1 plus I2. We're just using 2, but you could do it with 3 or 4 paths. But obviously for the proof, it's easier to do it with 2. So this is true, algebra. And then you know the total current must also be the total voltage, yeah, which is the same for both of them, divided by the total resistance, which we want to determine. So that means we know we can say that V over RT is a total current. We can then do V over R1 for the first component and V over R2 for the second component. And look what you have. You've got V over RT equals V over R1 plus V over R2. Guess what? The V's cancel out. So what is the equation going to look like? 1 over the total resistance must be equal to 1 over R1 plus 1 over R2. And this is the famous equation for resistors in parallel. Yet again, A-level students, you have to be able to derive this. GCSE students, you just need to know as much about this as possible, and you might be given an equation like that with a problem to solve in your physics paper. Okay, hope that makes sense. So remember, you can stop the video at any time, and you can make notes. That's the beauty of having my lessons on video. Okay. When I'm in school as well, I will try to upload these revision videos into Teams so you can watch them when you want to revise each section of the electricity topic that you've already done. Okay. So here's some problems for you to solve. You've got to calculate the equivalent resistances. So this one is 2 resistors in parallel. This is 3 resistors in parallel. This is 2 in parallel plus 1 in series. And this is 2 in series in parallel with another resistor. So these are common A-level questions, and they could potentially be GCSE questions as well. So far, GCSE students, you should stay with the course. Okay. Now, power through a resistor, also relevant for both GCSE and A-level students. So when you got power through any resistance, doesn't have to be a resistor, yeah, you should remember these equations. You've got the power equals current times voltage, and voltage equals current over times resistance. So you can substitute in the first equation using the second equation to get rid of one of the I's or the V's and come up with, yeah, 3 versions of the power equation. So you got the first one, which is IV, yeah, but you can substitute for the V with IR, so you get I times IR, you get I squared R. You can do the same by substituting for getting rid of I here by saying I is equal to V over R. You'll then get V squared over R as a third equation for power through a resistor. So these are all useful equations for determining power depending on which data you've been given in a question, for example. Okay, so for example, in question 1, they give you R and they give you amps, they give you the ohms and they give you the amps, so they give the resistance and the current. So you can go straight to I squared R to calculate the power, yeah? Which is the same as working out the voltage and then putting voltage times current. So this is a shortcut to the answer. And you want shortcuts in the exam, so it saves you time. And here they have a motor, they're giving the current, they're giving you the resistance in mega ohms. Don't forget, you have to change the prefixes to standard form, that'll be 10 to the 6th. So you've got the resistance and the current again, they're just giving you a more difficult version of it with the mega ohms in there. And again, you use I squared R as a one-step solution to work out the power. This time they're giving you the power and they're giving you the resistance, and they want you to calculate the current. So this time they haven't used V squared over R at all. In A-level they will use this as much as they use this. In GCSE they're more likely to use I squared R and P equals IV. So here they're giving you 2 kilowatts. Remember, kilo should be a small k actually, is 10 to the 3 watts. So it's 2,000 watts, 20 ohms. They want you to calculate the current which is basically just using this equation. So I hope that helps you. Yeah. And now the next bit is really for A-level students. So I think that's a good place to stop, pause, and then I'll continue for A-level students by going through what's called carrier density. And just so GCSE students get a taster for what A-level is like, I'll show you this slide, and then hopefully you found the video I've done for you useful. If you found it useful, please do give me a like, share it with anyone else who you think will benefit from watching these videos, and subscribe so you know when future videos are going to be uploaded. So the focus will be preparing GCSE students for their mocks in January, and for A-level students it's either revising Unit 2 or we'll do some other units as well. But this is electricity, so this is Unit 2. Some students are retaking this on Tuesday. That's the October Unit 2 exam retake. So you see carrier density. So those of you who want to leave now and you've given me a like and you've subscribed, this, if you want to stay, this is the A-level part only. So carrier density, for example, in copper is how many free electrons there are per atom. So you can work out, for example, the size of an atom is less than a nanometer. Yes, it's the order of 10 to the minus 10 meters. If you know the size of the atom, you can work out how many atoms there are in 1 meter, of length of 1 meter. Yeah, that means you should be able to also work out how many atoms there are in a cube of 1 meter cubed. So you can work out how many atoms there are, and you work out that there must be 6.4 times 10 to the 28 copper atoms using standard forms. And if each of those atoms has 1 or 2 free electrons, you can then estimate how many free electrons there are per meter cubed. And this is the beginning of A-level understanding of charge. So it's called the charge carrier density. The symbol for it is N, and you need to know how to use this equation. So I'm going to start another video with this at this point for A-level students only. Okay, for GCSE students, we're going to stop on power through resistors. So thank you very much for watching. Don't forget to like and subscribe, and see you in the next video. Bye.